Hello. We're going to do another problem that involves maximization, or actually minimization of cost. So let me read this problem. You have been assigned to design a box with a square base that must have a volume of 1,000 cubic centimeters. The top of the box will be made of gold foil and will cost $100 per square centimeter. The four sides will be made of brass and will cost $5 per square centimeter, as you can see in the diagram. What values of A and H will produce a box with the lowest cost, and how much will it cost? Now we've got to remember, we've got to keep the volume constant. The volume, of course, would be A times H. Okay, so the volume, which is A squared H, is 1,000. So as you make A bigger, H would be smaller, and vice versa. So let's take a look at this. Let's make an equation for the cost. The cost is equal to the surface area of the top and bottom times $100, and the surface area plus the surface area of the sides times $5. So C for cost is $100 times 2 for top and bottom, A squared, which is the area of the top and bottom, plus $5 times 4 sides, times AH, which is the area of each side. But as we see, the volume is constant, so that we take this equation and solve for H. H is 1,000 over A squared. If we plug that in for H, we get the following equation. C equals 100 times 2A squared plus 5 times 4 times A over 1,000 over A squared. Now the A and the A squared will cancel to give you 1 over A. So this is an equation for the cost. And you can see there's two terms. One term increases with the area. Of course, the cost goes up with A, rather. And one term decreases with A. Now, there are two ways to tackle this. If you know calculus, you know that if you have an equation that shows a maximum or a minimum, the derivative, the slope at the minimum, will be 0. So we could use calculus. But before we do that, suppose you don't know calculus, why don't we just use the spreadsheet and plot C as a function of A. Okay, so we have the plot here, cost in dollars versus A in centimeters, and you can see that it reaches a minimum and goes up at large and small values of A. All right, so I just plugged in different values of A, computed the cost. I actually figured out where the minimum was, and it turns out to be at 3.7 centimeters, and the minimum cost would be $8,143. Again, these numbers are just something I dreamed up. Probably not realistic, and I could actually change these numbers if the gold changed price. All right, let's now go to the calculus version of solving this equation. All right, so this is our equation. The cost is 200A squared plus 20,000 A to the minus 1/2. So if we take the derivative, dc dA, it's 2 times 200A, which is 400A, and minus 1 times 20,000 A to the minus 2. Now, to get A by itself, we're going to multiply both sides by A squared, all right, and then rearrange, and so we get 400A cubed, equals 20,000, and therefore A cubed equals 50, and take the cube root, we get 3.674, was 3.7, my other example. And if you want to get the cost, we have to find H, and we know that A squared H is 1,000, so H is 73.682 centimeters. You can see this is a long, skinny box, a high, skinny box, because gold is expensive. You're going to have a little bit of gold and a lot of brass. The cost, then we just plug in and we get 8,041, $143 as the cost. So nice little problem. Shows you the value of using a spreadsheet to find a minimum or using calculus. So thank you for your attention, and I'll see you next time.